Hey, everybody. It's great to see you all. How's everyone doing today? Have a good weekend? Yeah. Anybody do anything fun? I went swimming a couple times, making use of the last of the hot days of the summer. It's always nice. All right. Anybody have any questions for me? This time at the very beginning is a good time. If there's anything that you don't understand from the lessons or that you want more detail about from the lessons, or you want me to look up more information, this is a good time to ask. As I said last week, I don't want you to hold on to your questions until our class on Monday. Ask when you have them, but at the same time, this is a good time. All right. If you do not have any questions, we will go ahead and begin. Right. And always let me know if I don't have my screen on, if you do not see the picture there. So sometimes it does turn off. Sometimes I forgot to turn it on. All right, there we go. So we're going to talk a little bit about a little more today about what science is. But before we do that, I told you last week that soon I will be taking off points for spelling and grammar errors, and that will happen pretty quickly within the next week or so for when you have a written assignment. Now, I don't take off a lot of points. I'm talking about like a quarter of a point for a question that you might have. So I don't want to take off a lot because this is a science class after all. But it is really important that you learn and use proper grammar when you're doing school subjects. So when we have a chat like here in the classroom, you don't have to worry about it. You can use text speak there. When you write to me through Canvas inbox to ask me a question or answer something, get more information, that's fine. Whatever you want to use there is fine. It's only when it's a graded assignment, something that you're submitting for work, that I want you to make sure that you have proper spelling and grammar. Now, I have noticed a couple of common errors. So that's what I'm going to talk about today. Keep in mind, I only have 4 rules in my class for what I want in your written homework. There's a lot more to grammar than that, but these are the things that I'm going to be looking for that are important for what we're doing here. And I like this little reminder here that grammar can save lives. Let's eat grandpa or let's eat grandpa. One comma makes a difference between grandpa being dinner or grandpa being asked over for dinner. And our little panda friend here. A panda eats shoots and leaves. Unless it's a tactical panda, then it eats shoots and leaves, right? Comma makes a difference. All right, 4 rules. Number 1, capitalize the first word of every sentence, the personal pronoun I, and the names of specific people, places, and things. So always, always the first word of a sentence is capitalized. I don't want to see any lowercase I when you're referring to yourself. And for example, the question about Francesco Redi, both his first and last name need to be capitalized, and any proper names of places and things as well. So that's rule number 1. Rule number 2, use a full sentence. Don't just give me a phrase or a one-word answer. When you're writing an assignment, especially for an exam, you want to make sure that you use a whole sentence. So a sentence is a complete thought. Every sentence has 2 parts to it. It has the subject, which tells you what the sentence is about, and it has what's called the predicate, which tells you what the subject is doing or what's happening to the subject. Now, usually the predicate is a verb, like an action word. So we'll say a subject and a verb is what has to be in there. So I want to make sure that you always give full sentences and do not begin the sentence with the word because. It's really best not to. There are a couple of situations where it's okay to start a sentence with the word because, but it's pretty complicated. In general, the first reason is when you could use the word since, you can substitute the word because. Like instead of saying, since the plant didn't grow, I hypothesized that there wasn't enough water. You can use because there. Also, when you're having a conversation, like we're having here, when we're discussing something, a why question, you could say because, if I said to you, okay, why didn't the plant grow? You can say, well, because you didn't water it. So that is fine in conversation. But in a written assignment, don't start a sentence with because, and then end sentences with proper punctuation. So a sentence begins with either or ends with either a period or an exclamation point, and a question ends with a question mark. And that's really it. Those are the rules for my class. Capitalize useful sentences that don't start with because and end with punctuation. All right. Now, these are the most important ones. They're the ones I'm going to grade on. I'm not going to be taking off for other things as well. Spelling matters too. Use spell check if you're not a good speller. Again, if I can understand it, I'm not going to take off a lot of points. But if you're such a bad speller that I'm not going to understand what you're trying to say, you're going to need to use spell check to look that up. All right, please make sure that you are getting the announcements. If you didn't get the announcement about today's class to your email or to your parents' email, if that's what you're using, please go into the assignments in the course information module. It starts with the word urgent. It really is important. That's how I communicate with you. If ever there's an emergency situation and I can't come to class, that's how I'll let you know. Or if there's something that you need to bring to class, that's what I'll let you know too. When you are writing to me through Canvas inbox, be as specific as you can so that I can help you as quickly as I can. So let's say you've got a question about one of the quizzes. You've got a question about quiz number or question number 4 on quiz 3.2, making that up as an example. Don't just say, I have a question about today's quiz, because today is different for everybody. What you're doing today could be different. Tell me the name of the page in the book that you have a question about, the name of the lesson or the learning check question number. Basically, give me as much information as I can so I can help you more quickly. Don't just say something like, I don't understand question 4. Tell me what it is you don't understand about question 4 and what is the name of the lesson that question 4 is in. All right, speaking of being late to class, if I ever am late to class, the general polite rule of thumb with a class is to wait 15 minutes. If I'm not here within 15 minutes, then you can assume that I'm not coming. I've never had that happen in all the years that I've been teaching online. I always am here, or I let you know ahead of time if something comes up, which rarely happens too. But if I'm a little bit late because I have another class that goes over right before this one, then give me that 15 minutes just in case. That's a good rule of thumb. Anybody have any questions? Giving you a few rules at a time as we go through this. All right, so I have a couple questions for you guys just so we can get acquainted with each other. I'll ask a couple each week for the next couple weeks, and just for fun, get to know each other a little bit. So you can type your answer in the chat box. Everybody should be able to do that, should be able to type in the chat box, I think. Hold on, let me get it turned on here. Yep, there we go. All right, so using just one word, what makes you happy? One word. What's the first thing that comes to mind when you think, what makes me happy? Dancing, sun, music, books. Great answers. All of those make me happy. Hugo. Art. What's Hugo, Stella? What do you mean by that? Is that your pet? Victor Hugo, the author? Your dog. Okay. Dogs. Yeah. Something about a dog, boy. Any kind of pet, really. You can't be unhappy when you got a pet sitting on your lap or licking you in the face. All right. Next question. Describe yourself using just one word. It's a little deeper, isn't it? Just one word. Don't have anybody answering that one. Nobody wants to pin themselves down to just one word. All right, how about 2 words? What and what? Clever. Clever is a good thing to be, Carson. Witty. Busy and fun. Yep. Excellent. Kind. Love that. We should all strive to be kind. Curious and interrogative. Interesting. And creative. Awesome. Awesome. All right, here's your next question. This is a little easier. Your least favorite food? Tuna. I love tuna. Isn't it funny how we all like different things? Brussels sprouts, that's a common one. Tomatoes, garlic. Ooh. My rule of thumb when a recipe calls for garlic is triple the amount of garlic and then add more garlic. I love it. Kale? Yeah, kale needs a little bit of attention in order to be good for you, in order to taste good. You have to either cook it or shred it or something. All right, next question. If you could have 25 hours in each day, what would you do with the extra one? Read, sleep. Yeah, sleep's a common one. Ballet. Yep. If it makes you happy, do it more, right? Exercise or read a little bit more. Very good. Great answers. All right, here's a fun snuggle your dog. Snuggle with Hugo or play hockey. Go to school. Cool. Good answer, Kate. All right, how about this one? It's a fun one. If you could be in the Guinness Book of World Records, what record-breaking feat would you attempt? That one's not easy either, is it? Long jump, swimming, swim the longest, have the longest hair, have the longest fingernails, tallest high dive, traveling to the most countries in one day. Wow. You'd almost need some kind of transporter in order to be able to do that. Chess matches lost in a day. Oh, Ben, no. How about chess matches won in a day? Largest crochet piece. Wow. What's the biggest thing you've made, Ella? A blanket? Have you made blankets? You made a king size blanket before? That takes forever. Most books read in a year. That's a good thing to keep track of. Keep track of the number of books that you read. Here's what I recommend. If you read a book, have a journal, like a page or a website or something, a document on your computer where you write down the name of the book, whether you liked it or not, and a little short synopsis about it. Because sometimes you get to where you're like, I can't remember, especially if you read a lot of books. I read a lot of books, so sometimes I can't remember if I've read it before. So it's nice to have that document. All right. One more, two more actually. Using just one word, name something that drives you crazy. What drives you crazy? Homework. Chewing, like somebody chewing too loud when they're eating. Yeah. Yeah. Spiders, bugs. Mine would be traffic. Yeah, too much traffic. My sister. Yeah, well, siblings almost always turn up on these lists because they do drive us crazy. Eventually, they become your closest friends, but it takes a while to get there. All right, last question. Name one step in the scientific method. Anyone. There's usually 6 or 7 of them. Talked about them all last week. Observation, experimenting, hypothesis. Excellent. Great. All right, so we are going to talk a little bit more about the scientific method today. I want to talk first about this lab that you have coming up. So it's this week that you'll do this lab, and then next week, your first lab report is due. So in our live class next week, we're going to talk about how to write up a lab report. So you'll do the lab this week, taking notes as you do. Next week on Monday, we will talk about how to put together the lab report, and then the report will be due on Friday of next week. So that gives you plenty of time. So what I want to do today is quickly walk through the steps of the lab so that you do the lab itself correctly. Now, when you are doing any kind of a lab procedure, always begin by reading the entire thing. Read all the directions start to finish so that you know what you're going to be doing, you know what you're going to need. That's true of a recipe too. If any of you cook, it's a good idea to read the whole thing, because otherwise you get halfway through and say, oh man, I don't have this ingredient. If you read it start to finish, you know what you're going to do and what's required. So always read over the directions. The second thing that you always want to do when you start a lab is to gather all your materials before you begin. Make sure you have everything there that you need. So these are the things that you're going to need in order to do this lab. You're going to need a small package of Jell-O. Now you can also just use plain gelatin. I put that in the lesson. When it says frozen pineapple, you can take fresh pineapple and freeze it. That will work too. It just needs to be frozen until it's frozen solid. And then you guys can read the rest of those when you're looking at it. I'm not going to go over the instructions because there's a lot of them right there and you can read them as you do them. Just make sure that you follow them exactly the way they are written. Make sure to start at the top and work your way to the bottom. Don't skip any steps, because skipping even one step in any kind of a lab procedure will throw off the rest of the lab. And you'll use a chart that looks like this to collect your data. So I have this chart in the lesson. You can print it out, copy it onto paper. Just make sure that you keep your data sheet, that you bring it with you to class next week, because we're going to talk about the results. And we'll talk about how to write up the lab report based on the experiment you did and the results that you did. All right. Anybody have any questions about that lab? I don't know if you've looked ahead and you know that's coming, but it's due this week. So always at the beginning, I've got a master supplies list in the course resources. And also at the beginning of each week, I have a list of the materials you'll need for that week. So if you look on that, if you looked before, before this week, before Monday, you'll see the materials that are needed for this lab. Most of the labs, most of the activities and projects and labs are optional. Please do them if you can. You really do learn a lot, but I'm not requiring a lot of them. And when they are required, it says very specifically required right in the title of the thing. So you know that it is a required activity or lab that you have to do. All right. We won't spend a lot of time talking about the periodic table because you'll get to that in future chemistry and physics classes. But it's important to learn that everything in the universe, including all living things, are composed of some different combination of these elements. Now, there's 118 of them on the periodic table, but only the first 91 are found in significant amounts in nature. The rest of them are either made in a laboratory or are found in very, very, very tiny amounts in radioactive chemicals. So 92 to 98 are found in nature, but only in radioactive things and only in very, very small amounts. So of those first 91, take a look here and see where the numbers are. So see, this is a 65, 66, 67. So if we go here to 89, 90, 91, only these first 91 are found in nature in significant amounts. And of those 91, 4 make up about 96% of everything that's living. Anybody have a guess which 4? Which 4 elements make up the 96% of living things? Just guess one. You don't have to guess them all. Kate.
Carbon.
Carbon, yep. Carson.
Hydrogen.
Hydrogen. That's 2. Reagan.
Oxygen.
Oxygen. One more. Nitrogen is the 4th. Sorry, Carson, I didn't see your hand in time. So hydrogen, carbon, oxygen, and nitrogen right there are circled. Now, most of the remaining 4% of an organism's weight is made up of phosphorus, sulfur, calcium, and potassium. So there's phosphorus and sulfur, calcium, and potassium. Right there is almost everything that living things are made of. Now, there's also some trace elements. There's things like iron. You know that because you have to have iron in your blood. That's one of the reasons that we eat iron-rich foods, is to get the iron that we need, because our blood cells need iron in order to carry oxygen. There's things like copper and zinc and iodine, but they're present in really, really small amounts. So small, they're called trace elements. We'll talk a lot about this when we get to the human anatomy section, the human biology part of our course. But this all applies to all living things. So of all living things, 96% is made up of those four: carbon, hydrogen, oxygen, and nitrogen. Right? Now, you'll notice when you get to the lesson about carbon compounds that I put a video of a song to help you learn the periodic table of the elements. If you want to learn the names of all of those, there's a song in there that'll help you learn it. And if you're interested in memorizing the periodic table, that song can really help you. Now, it's not required. You're not required to memorize the song. But if you do, if you memorize it and you sing it in class, I'll give you 20 extra credit points. That's a lot. That's like 3 quizzes worth of extra credit points. Just memorize it on your own and send me a Canvas inbox message when you're ready, and I'll fit you into the next class, right? Any of you guys already know it? Anybody know the periodic table song or sing it? Well, guess who does? Harry Potter does. So not Harry Potter himself, of course, the actor Daniel Radcliffe. He did a game show or a talk show one time where he sang the periodic table, and I thought you guys might enjoy that. It's kind of fun.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and anthium, and osmium, and acetine, and radium, and golden, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and iridium, iridium, and strontium, and silicon, silver, and barium, bismuth, bromine, lithium, beryllium, and barium. And let's start the next verse. There's holmium, and helium. There's holmium and helium and apium and erbium, phosphorus and francine and fluorine and terbium, and manganese and mercury and molybdenum, magnesium, dysprosium and scandium and cerium and cesium. There's lead, praseodymium, platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arsenium, nobelium, and argon, radon, neon, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arsenium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
kind of impressive. All right, so 20 extra credit points if you can get that. All right. Now, last week, we learned about some science basics, and we talked about the scientific method. I want to talk a little bit more about it today. There was a section in your reading that was called Thinking Like a Scientist. So I want to talk about that, what thinking like a scientist means, because really, there's a lot of problems in life that can be solved if we just think like a scientist. When we're trying to solve any problem, from I lost my favorite bracelet in my room to I've got to get all this homework done and I don't have a lot of time. If we go about it in an organized, structured way, we can often solve the problem. So we often will start with an observation, and we want to observe details. So imagine that you're sitting in this dentist chair here. You're going to be waiting for 30 minutes, and the dentist then is going to arrive in 30 minutes. So what are some things that you might observe in this room? Tell me what you observe. If you were sitting in this room, excuse me, what would you be observing? The light above the chair. Yep. What else? Lots to observe in there. And you're not just looking at a picture of it. You're actually sitting in that chair. What's outside the window? Good. Reagan.
The TV.
Yep. Yep. There's definitely a TV up above. What else? Brainstorm here. Yep. So what the chair is made of, you would be observing like what it felt like. Remember, when we observe, we use our senses. So observation comes with either the senses or some tool that enhances your senses, like a microscope or a telescope or a computer. The floor, yep. Be looking at the pattern on the floor, the texture, the smoothness, shine. Lots of things to observe about the floor. Temperature in the room for sure. So you'd be using your sense of touch for that one. Is it cold in here? It's usually cold in a dentist's office. Is it warm? What other senses might you be using besides just sight and touch? What it smells like. Yeah, there's a smell to a dentist's office, isn't it? They all smell the same. So you'd be smelling that. Any sounds, right? So there could be the sound of people walking by in the hallway. There could be the sound of the ventilation or the drill in the next room. Those are some things that you might observe. So once you've observed something and made that observation as detailed as you can, then the next thing you do is ask a question. But we want those observations to be as detailed as they can, because that will help us to design our experiment. So using another scenario here, imagine that you're a scientist and you're out in the jungle and you observe in this jungle, on one side of the jungle, on the north side, the elephants are healthy. On the south side, though, there's a group of elephants that are dying mysteriously. We're not sure why. How could we make that observation more detailed? How could we narrow that down rather than just say, oh, I observed that they're dying? What else could we observe that might lead us to the kind of question that we want to ask, which would lead then to an experiment? Carson.
The environment.
Yeah, we would want to look at the whole environment. And there's a lot to the environment, like what plants are there, what predators are there, what's the rainfall like, what water is there? Are there some poisonous plants that they're eating on the other side? Yeah, there's a lot that we can narrow down in the environment. Okay, what about the elephants themselves? Is the water they're drinking diseased? Yep, yep. Does it have some kind of parasite in it that's getting to them? What about the elephants themselves? What could we observe about the ones that are dying? What might we want to know about them? Yep, they could be sick. What, are they dying because they're sick? Or are they dying because they're being killed? Are they thinner? Yeah. Are they losing weight? How about their age? We would look at this differently if they were all old than we would if they were very young. We would approach the whole thing differently. Also, male and female. If it's only the males who are dying or only the females, we're going to approach the situation a little bit differently. So the more detailed we can make this, the better. Once we have a detailed observation, that's then when we start asking questions. Often questions begin with these kind of words, the question words, but we want our questions to be as specific as they can too, because remember that these all kind of lead into the next one. Observation leads into questioning. So the more detailed we can make the observation, the more concrete our questions will be. The more detailed we can make our question, the more specific we can make our hypothesis. So what are some questions based on some of what we thought we might observe, the detail we might observe, the age, whether they're losing weight, what the environment is, male or female? What are some questions that we might ask based on those particular things? Let's just focus on the environment. Let's say, you know, put that in there. What are some questions we could ask about the environment? You guys can talk. It's faster if you do. Well, the environment would be composed of plants, other animals, and water and shelter, right? So we know that elephants are herbivores, they eat plants. Maybe there just isn't enough plant food on one side of the jungle. So let's say that that's what we focus on. Let's say that we come up with a hypothesis that says, you know, there's not enough food. There's just not enough food for them. How could we test that? How could we see if that's the problem? Kate.
We could just go there and look around to see how much of the plants that elephants can eat are around that area.
Good. So that would be in the observation area again. So that we definitely would want to do that. And once we do that, once we look at the plants and we say, okay, are there enough? Then let's say that we looked and we said, it doesn't look like there are enough plants on the side where they're dying. So that's kind of an observation that we made. That's a question. Are there enough is there enough plant matter for them to eat? That's a question that we could ask. So then a possible hypothesis would be that there isn't, you know, that maybe we hypothesize that there isn't enough. So how could we test that? How could we test whether they're dying because they don't have enough food? What if you're cranky and your mom thinks it's because you're hungry, what does she do? Carson.
You could feed the elephants.
Yeah.
And see if they get better.
Yes, that's a good way that we could do that. We could provide food and see if they get better. Now, another way, we could go the opposite. We could take food away from the healthy ones and see if they start dying. But we don't like to do that in science. We don't like to do things that cause harm to living things. So we want to focus on the positive. So we want to focus on helping rather than hurting. So we're going to go with giving them more food. So now let's turn that into our hypothesis. Remember that our hypothesis has those two parts, the if and the then. It has the statement followed by the prediction. Now, what's really confusing about this is that the statement is called a hypothesis and so is the whole thing. So really it should be called a conditional statement, but we call it both of those hypotheses. So if we did our if then hypothesis for this scenario that we just talked about, what would it be? If I do something, then something will happen. What's the if part of that? If, Kate.
If I feed the elephants, then they won't die.
Very good. Yes. If we provide food to the elephants. Excellent. So that's the independent variable. If we give them food, that's the independent variable. Independent variable is the one you change. It's what we're changing. Then we're going to measure something. We're going to measure whether or not they die. That's our dependent variable. If we give more food to the elephants, then they won't die. So again, the real beauty of writing your hypothesis in if-then format is it tells you what your experiment is. It suggests your experimentation and it tells you what you're going to look for. So we would set up an experiment to test and see whether or not our hypothesis is accurate or not. So if we wrote that hypothesis in if-then format, we know what to do, we know what to look for, then we get our data, we get our results. When we get our data, we want to always question the answers. What does that mean, to question the answers? And you guys heard the term skeptical before? Yeah, skeptical just means that you're suspicious of an answer. Not necessarily doubting, but you want more. You want more. I'm skeptical. I want more information. So good scientists are skeptical, and they never use one piece of evidence to form a conclusion. Because let's suppose that we put food in the jungle and the elephants stop dying. Do we know for sure that it was the food, even though we only have that one variable that we changed? Do we know for sure that it was the food that kept them? No, it could be something else. Maybe they were eating some kind of food that was toxic to them, that was poisonous. Now that we've given them food, they've stopped eating that toxic food. They're only eating the food we gave them. So we don't know for sure. We have to run more experiments. We also have to find other scientists to run experiments too, to either confirm or disagree with our evidence. So then after we have gathered our data, questioned our answers, maybe run a couple of more tests, then we're going to come to a conclusion of some kind. If our hypothesis supports our conclusion, then great, we're going to publish our results. I'm sorry, if our data supports our hypothesis, then we're going to publish our results. If it doesn't, we're going to go back to the drawing board again. All right. So we encountered this word here. Sometimes this can be a little bit confusing, the word theory in science. I know it was in your book, but I want to make sure you guys know how a theory in science is different than the word theory in life. When we hear the word theory, we often just think that somebody's guess about what happened. But a scientific theory is more. I have a theory that the platypus predicts the weather. Our kind of theory in common life can just be a random guess about something, but that's not what it means. In science, a scientific theory is an explanation supported by a lot of evidence, usually a lot, usually well-established and well-tested evidence. So theories are developed when experiments are repeated and repeated, often by many different people. So an example would be the theory that matter is made up of atoms. That's a scientific theory. And we accept it as a fundamental principle of science, but sometimes scientists find new evidence that will change their theories. You encountered one of those last week when you were reading about spontaneous generation. So that's the theory that living things came from non-living things. And it's not really surprising that people before the invention of the microscope thought that. From their point of view, kind of looks like that happens in my kitchen sometimes. All of a sudden there will be fruit flies. Where did they come from? Well, they must have come from the rotting fruit. So they just spontaneously appeared. Well, we know that's not true because of the experiment done by Francesco Redi. He did the first one where he put the gauze on top and then they couldn't get in there. So he disproved spontaneous generation. And then Pasteur came along and he did more to disprove spontaneous generation. But taking a look at Redi's experiment here, what do you think his hypothesis was in if-then format? Remember where if is what you do, then is what you look for. What could his hypothesis have been? If, Ella.
If I cover the jar, then there won't be maggots.
Very good. That tells you what you're going to do, tells you what you're going to look for. So what would his independent variable have been? Toby.
The gauze.
Yes. What was his dependent variable? Reagan.
The open jar.
So the open jar would have been the control. Remember, independent variable is the one you change. Dependent one is what you measure. So if gauze on the jar is what he did, what was he looking for? What was the dependent variable? What he was looking for would have been the presence or the absence of the maggots. They either were there or they weren't. In this case, it would be the absence of the magnets. And then everything else was kept the same. Everything else was controlled. Now, he also had the control group and the experimental group. So the control group was the one that he didn't change anything. He didn't make any changes. That would have been the open jar. That was what people had always done. Open container, food's inside. He was trying to change something to disprove spontaneous generation. He did the gauze and he did the parchment. And then, of course, Pasteur with his curved neck flask did much the same thing. So there's another theory that has been disproven. This was really popular back in the 1600s. It was called the blank slate theory. And people really believed that babies were born with nothing. They were complete blanks. They knew absolutely nothing. The only thing that they got came from experience. So you can kind of see why they might have thought that, because, babies just kind of lay there and they don't do anything. But we know now that genetics plays a big role. Family traits that are inherited from both of your parents play a role. And there's also some instincts that babies just have. Those play an important role. So an instinct that a baby would have is when you put your finger on their palm, they close their fist. When you run your thumb up the bottom of their foot, their toes flail out. Yours don't do that, but babies do. Babies have a startle reflex. where if somebody makes a noise, their whole body kind of shakes like this. That's usually only there for a few weeks, maybe a couple of months at most. You don't do that. You might startle a little bit, but your whole body doesn't shake like a baby does, like the startle reflex. So we know the blank slate isn't true. That theory was disproven. We do, though, have some really important theories that, at least for now, at least based on what we know right now, are true. And one of them is called the cell theory. We'll talk a lot about the cell theory throughout our course, and when we get into, especially when we get into talking about cells in a couple weeks. The cell theory tells us three things. Every living organism is made of one or more cells. So if something is not made of cells, it is not alive. Clear as that can be. Viruses are not made of cells. Are they alive? No. So there are some scientists who are arguing that we need to change the cell theory in order to fit viruses, because viruses behave in a lot of ways like living things. But as of now, trusting the cell theory as we do, accepting as that as it is, viruses are not living things. They are not made of cells. All cells come from pre-existing cells. That means no spontaneous generation. You have to have a cell in order to get another cell. And cells are what does life functions. That's what the third one there. Basic unit of structure and organization. Basically, you can just think to yourself, cells perform life functions. Those are the three parts of the scientific method. And that's an important theory. That's one of the basic tenets of biology, is the cell theory. So we will, we'll become very familiar with cell theory as we go through our course. All right, now back to the scientific method. So one of the most important things about this scientific method is it allows one scientist to reproduce another scientist's experiment. These are the steps. You'll see more and fewer listed, but knowing the scientific method is important for a lot of reasons. One is that it is the format that we will use to write a lab report. And lab reports are not something that you just do in high school or college. If you go into any kind of science field, you will have to publish your findings. You do that in the format of a lab report using the scientific method as your base. So knowing these steps will help you as you write your lab reports. You'll do 2 lab reports each semester in this class. You'll become very familiar with writing lab reports. All right, so the very first step in the scientific method, observation, then question, hypothesis, experiment, analysis, and conclusion. And sometimes right here in between question and hypothesis, there will be research. You might go to an expert to try to find out if somebody else already has answered your question. So let's use a cute little scenario of a toaster to walk through these steps of the scientific method. So suppose you get 2 slices of bread, you put them in the toaster, you press the button down, but your bread doesn't toast. What's your observation? Reagan.
The bread hasn't toasted.
Yeah, exactly. The bread hasn't toasted. We could say the toaster won't toast, whichever we want to put it on. But yes, that's what we observe. We observe that with our senses, with our eyes, with our fingers when we touch the bread and it's still cold. With our smell, we're not smelling toasting bread. Take a bite of it, toast tastes different than bread. So your senses would tell you, my bread did not toast. So the next thing we're going to do then is we're going to ask a question based on our observations. Now, we might ask a question that's as simple as, why not? Why won't my toaster toast? But we want to get more detailed than just why. We want our question to examine possible reasons why my toaster won't toast. So there are other questions that we might ask that would be a little bit more detailed. Any thoughts? Kate.
Is the toaster not toasting because I forgot to plug it in?
Good. Excellent. That's much more detailed than just why isn't it toasting? Now, what else? What other possibilities are there?
Is my power out?
My power out. Yeah. Good. All right. So we want it to be a testable question. It has to be something that we can run an experiment about. So it can't be something like my toaster doesn't like this brand of bread. That's not valid, right? It can't be, you know, an alien snuck in and changed my toaster's method of working. I'm grasping at straws here, but it can't be anything like that. Now, the next thing we could do after asking our question is we could do some research. You don't always have to do research. Sometimes you already know what's going to happen, but sometimes you do. So there are ways that we could do research, finding out why the bread isn't toasting. We could go online and say, why might my toaster not be toasting my bread? You could yell to your parents, hey, mom, dad, the toaster isn't toasting, and they might offer a suggestion to you. Basically, what you're doing when you're researching is you are looking for someone who has existing knowledge about that topic. Then after doing any kind of research, we're going to put together a hypothesis. Now, the more specific we have made our question, the better. So remember that a hypothesis is a prediction of what we would expect to see. And whenever we can, we want to write it in that if-then format in a way that is testable. So with if being what we're going to do and then being what we're going to look for, let's talk our way through this one. If the first part of our hypothesis, that first sentence is maybe the outlet is broken. That's the one we're just going to choose for here. Maybe the outlet is broken. The second part would be then that's our prediction. If I plug the toaster into a different outlet, then it will toast the bread. So in this one, in this number 4 right there, if I plug the toaster into a different outlet, then it will toast the bread. What is the independent variable? Independent variable is the one you change. Toby.
The outlet.
Yep, using a different outlet. What is the dependent variable? Toby?
The toaster.
Yeah, no, not the toaster. The dependent is what we're looking for, what we're measuring. Carson?
Whether the bread is toasted or not.
Whether the bread is toasted or not. Now we got a whole bunch of controlled variables here too. We have to control everything else. The only thing we want to change is that outlet. We don't want to change the brand of bread. We don't want to buy a new toaster. We don't want to have a different person doing the experiment. The only thing we want to change is that one variable, the independent variable, plugging that toaster into a different outlet. Now, not every kind of hypothesis has to be in if-then format. So here's an example of one that doesn't. We know that drinking sugary drinks every day can lead to your teeth decaying. That all by itself would be a valid hypothesis. Consumption of sugary drinks leads to tooth decay. That's not written in if-then format. So you can have a hypothesis that is not. But I want you to use it as much as you can because it's a really valuable way to think about science. I think it's a good habit to get into. Can I write this in if-then format with if telling me what I'm going to do, then telling me what I'm going to look for? So if is my independent variable, then is my dependent variable. So that's an example of when you wouldn't have to do that. All right, so in this case, our if-then hypothesis for our bread problem could be, if I plug the toaster into a different outlet, then it will toast the bread. We want to then do our test. We're actually going to do the first part of our if-then hypothesis. We want to change nothing else. Any variable, what we mean by variable is just something that can either change or be changed. The controlled variables, they could be changed or cause change, but we're going to keep them from doing so. So in this case, what we're going to do for our experiment is we're going to plug our toaster into a different outlet, and then we're going to try again. We're going to control all the other variables other than the new outlet. Then we're going to analyze our data. If we plugged our toaster into a new outlet and the toaster does toast, our hypothesis was supported and is likely correct. We'd probably need to run that experiment a few times before we could for sure say that it was true. If the toaster doesn't toast, then the hypothesis is not supported and it's likely incorrect. Then we would need to go back and write a new hypothesis. Maybe it's the toaster itself that's broken. Maybe we don't have power to our entire house. So once we have analyzed our data and drawn a conclusion, if our conclusion supported our hypothesis, the very last thing that we're going to do is communicate our results. So scientists might talk to a group of other scientists. They might write an article for a journal, or they might talk to a journalist who would then write about it themselves. But that's the final step, would be coming to the conclusion and then communicating the results if needed for this. Now, a couple things about a scientific hypothesis. I want to think this through for just a second. It has to be falsifiable. That's an interesting term, isn't it? Falsifiable. It means it has to be able to be proven wrong. What do you think of that? If a hypothesis can't be proven wrong, but we treat it as valid anyway, that could really negatively affect the whole scientific process. So think about the implications if hypotheses that can't be proven wrong are treated as valid. Then anybody could just guess anything, and there's no way to prove that it's wrong. There's no scientific way to prove that it's wrong. If a hypothesis can't be proven wrong, it can't be tested. That means really no new knowledge or understanding could come from that hypothesis. And that could lead to scientific progress being slowed down. It could lead to people not even trusting in science in the first place, because I can say anything and it can't be proven wrong. So there you go. So we need to make sure that our hypotheses are always falsifiable. Now, there are some examples of hypotheses that are not falsifiable. Can anybody think of any examples? Things that are not falsifiable, so they're different. Toby.
Anything like having to do with like emotion, I guess,
Yeah.
can't be tested.
Yeah, so remember, science has to do with the physical world. It doesn't have anything to do with hopes and dreams and fear and anger and love. It doesn't have anything to do with any of those. So anything that I come up with that is a hypothesis that's related to any of those is not, that's not falsifiable. So that's going to be different from a scientific hypothesis. However, there are some fields like theoretical physics, social sciences. So those would be like psychology and economics, history, politics, political science. Those are sciences, but they're not ones where you can come up, a lot of times you can't come up with these hypotheses that are able to be falsified. So what challenges do you think there could be in these areas, in using science in these areas? Toby.
I guess like proving that they're right or getting people to acknowledge it.
Yeah, because you can't prove that they're right. If you can't prove a hypothesis wrong, you then can't prove it right either. So with a lot of these kind of fields, things like theoretical fields, artificial intelligence has, plays a lot into this one. We have to speculate a lot of times, and we have to just accept the fact that we have some gaps in our knowledge. There are some things, yes, these are sciences, but they're not things that we can prove or disprove. So it's there's a little bit of a challenge in those kind of fields. And what ways might the necessity of being falsifiable limit the scope of scientific inquiry? We kind of talked about that with the last page too. It's limited because there are some sciences where we can't make something falsifiable. So we just have to accept some of those and know that, okay, in these fields, in this narrow range right here, we're just going to have to go with what we think. One of them is the idea of the subatomic particles. When we get down to talking about things that are below the level of the atom, a lot of that's theoretical. We're not completely sure. It looks like it, but we can't really prove that it's false. So a lot of that, we just have to accept it. And are there areas of research where this criterion might be too restrictive? And how should science navigate these challenges? So yeah, there are some areas where it's too restrictive. So things like consciousness, the purpose of life. Why are living things living? Those are things that are often outside what we can consider falsifiable hypotheses. So we have to often consider those things beyond the scope of science. That doesn't mean the science doesn't have anything to do with it. It just means that they don't fall into the traditional scope of science. And we are out of time for today. Anybody have any questions? I hope this is all making you think a little bit. That's my goal here. All right. If you have any questions, write to me. If not, I'll see you next Monday. Have a great week, everybody. Thanks for coming. Thanks for the conversation.
Bye, thank you.
Bye.